Speaking of reliability, a podcast with good friends talking with you about reliability engineering topics. Welcome to Speaking of Reliability. This is Fred Schenkelberg.
And this is Chris Jackson. And Fred has cornered me and wants to talk about math today, or mathematics. Or
Maths. Yeah, I had that quick, just the thought is it, because I've heard it in, I don't know if it was Australia or England or whatever, they talk about maths, like the maths with an S, math plural class. And I realize that it's math and maths is just short for mathematics. So like whatever. But anyway, what I want to mention is that I did a webinar a couple weeks ago, and it was sparked because I got a question about how do I interpret these metrics that are in a software package looking at a Weibull regression. And I said, well, did you plot it? Did you see the graph with the data on it? Oh, you can do that? Okay. Yeah, let's go do that first. And it was, but then it became a question of, well, what is this Anderson-Darling thing? And what's this maximum likelihood value? And what's this number? And why do I care? And all that stuff. And so that ended up being a much longer conversation. But then I said, well, since I looked at all this stuff, let me do a webinar on it. And I basically, correct me if I'm wrong here, Chris, but I basically said, don't pay attention to R squared and Anderson-Darling and all these other things, unless you know exactly what those things are and what they're for and how they're used. And that takes some study. Instead, plot it, put the data on the curve and see what it looks like, and then look at the residuals, those differences, because that reveals things that you can't see on a probability plot as clearly. And then make your judgment. But was that, I'm hesitant only in that, was that folly?
No, I mean, the analogy I use is the sporting combine. So at least in the United States, a lot of professional sports involve athletes coming straight out of college, for example. And one of the more popular things to do is have what's called a combine, where all these athletes who are about to be selected in drafts or signed to professional contracts, they go to a central location and they do specific drills where they are measured or timed for how long they take for them to sprint 40 yards. Mm-hmm. And so just take, for example, the NFL. So the NFL combine involves a 40-yard dash, and some of the really fast times are 4.2 seconds and slower times are 5 seconds, et cetera, et cetera, et cetera. Mm-hmm. Why I'm using that analogy is because it's like a professional football team not looking at individual players as they play on the field, not looking at any tape, any videos, or observing how they played on the actual football field themselves to see if they are good football players or not, and simply deciding on whether to sign those athletes up based on their combine performance. So they just a team that would hypothetically simply sign up the athlete who had the fastest 40-yard dash, or the athlete which had the highest vertical jump, et cetera, et cetera. Mm-hmm. Everyone knows you can't do that. You can't just simply find the most impressive athletes in terms of how they're measured on that particular day and assume that they are going to be the best football players on the field. Kevin Durant, he's a basketball player. Very famously, he's a very thin man, but is also one of the most dominant scorers in basketball in the history of the sport. But he had very poor bench press results during his combine. Mm-hmm. So why I use that analogy is because those Anderson-Darling metrics and p values and rho values and everything else, they're like the scores or the times that athletes get at NFL and basketball and football combines. They, as a rule, the better players will perform better, but that's as a rule. But it never replaces actually observing how that player performs on the field, how they perform during their college careers. There is no way known you should ever select a football or a basketball or a soccer or any sort of player or athlete based on, especially if they're playing a team sport where there's a lot of skill involved, based on simply their scores or times at a combine. So when you go back to software, unless you're plotting that data and actually looking for characteristics that you as a statistician should be aware you need to see in data which has a good fit to an underlying model, you're just going against these numbers. And those numbers are inherently meaningless depending on the scenario you're investigating. So that's the analogy I sometimes like using. Do you choose football players or soccer players or basketball players based on how high they can jump and nothing else?
Yeah.
No, of course you don't. It has to be everything else. And you would argue that perhaps the combine scores or the times confirm certain things that you've already deduced through your own analysis. So when it comes to goodness of fit, you'd want to see certain characteristics on the plot before you go to these numbers and say, yes, that looks like it fits based on my assessment, and these metrics seem to be where they need to be. Therefore, I can assume that this model is good to go.
Yeah. Well, it might explain part of why my data analysis professor way back when I showed him one of these wizards, the software package had just come out with, I think they had 8 different software distributions, and it would on one button fit all 8 and then run, I think it had Anderson-Darling was in there, maximal likelihood something was in there. And there was one other one. I think it was Row, or some fancy name for it. And then they would say, this one has, on average, the best metrics. And so that must be the right fit. And he looked at that and just said, that's just evil.
Yeah.
It's just, and because it goes to your point. It doesn't, each of those measures, and the more I learned about them over the years, is they had completely different purposes. You know, one of the measures is to compare to. The number itself had no meaningful value. It'd be minus 2,000 or it might be minus 20. But if the one you're comparing to it is minus 20 versus minus 40, then the minus 40 would be just explaining more of the variability than the other one, independent of whether it was actually a better fit or not. It just said it explained more of the variability compared to that. But if both models were bad, you're getting pretty bad information. It doesn't mean it's the best. It's not the right. It doesn't give you any of that stuff. And same for each of the measures and metrics that are out there. It's like R squared. Just add it, if instead of a 2-plot or a 2-point or a 2-parameter Weibull, do a 3-parameter Weibull. R squared will get better. Whether it's whether it's useful or not, it'll just get better. You until you add 15 more variables to it, it'll be perfect.
Right.
Totally meaningless model, but it'll be perfect.
Yeah. So, I mean, there's no problem in adding a 3rd parameter to the Weibull if you know that there's some underlying mechanism behind it. So if there is some hard and fast minimum value that you can't go below, that's okay. There's some information behind that assumption.
I had that in a expert witness. I was on a case, and the data was that the opposite side had was a 3-parameter Weibull, and it went negative 4 months. I'm like, that's before they even got the raw materials to make this thing. How in the world can you have a model that predicts it failed before it was conceived? You know,
right?
Statistics, yeah, it's a better fit, and they were touting the R squared value and this, that, and everything. I says, well, that really is pretty meaningless. This just doesn't fit. So at some point, there's a bit of common sense, and I think the understanding the model fit is the phenomena and the behavior of the characteristics of your data set and the models that are meant to model that behavior. There's some phenomena there, and some are just purely empirical, but be honest about it, that no, we just tried things and this looks best, But then even given that, then you start looking at, well, how does it look on a plot? How does the data look versus the fitted line? How does the residuals, do they fan out, or do they undulate, or do they suggest that you're missing something? Did you look at those? And then my favorite way to check a fit is we'll leave out 5 of the points and fit your data and then see if they predict where those 5 points are. How well does it do what it's supposed to do? Or if you're doing reliability work, fit your data and then you get more field data the next month. And does it line up? Does it fit? Does your model actually predict your future and get some feedback on it? Instead of just taking the new data and write a new model and never use it. I always wondered why people would do that.
Yeah, and if you think about it again, so if you know, for example, that your data is modeling time to failure, or based on time to failure for something that fatigues, you should automatically know that there is something wrong if your software says the exponential distribution is the best fit.
Right.
So that is something that you need to have in your mind, that level of awareness, skill. What do we want to call it? A number that a piece of software spits out should never be the one and only thing you base your conclusions on. If you don't know why the exponential distribution is not the right fit for something which fatigues, then I'm sorry, you're not qualified to drive that software.
Yeah. And part of it is that, I took a chemistry class in high school and I had a slide rule, and it was part of the class was learn how to use the slide rule. And then one of the kids in the class got a calculator. I think it had add, subtract, multiply, divide, but it had logs on it. You could do logarithms. And it was probably, at the time, it was probably a $500 calculator, which none of the rest of us could. We were all wowing and everything else on it. But one of the buttons, when he pushed the 3, it would turn into a 5 on the screen, and we'd calculate out like a 5. For some reason, that was shorted or wrong, or software was screwed up. And so we all laughed at him. And we had races where he would calculate stuff and double check his numbers. And we'd do stuff on slide rules, and we could beat him at it and the speed of it. But my takeaway is that just because you could push the numbers and you get $4.18, sir, and here's your change, you better do some quick math real quick at that checkout. Was that machine right? And I've never lost that mistrust. I'll run a known problem through those software packages. Do I get the answer I expect? Now I'll go look at my real data, kind of thing. And then even with the real data, I still go look at a bunch of other stuff to validate the model. And just way too many times I've run into people go, well, there's the answer. How do you know? Where'd that come from?
Well, as a rule, if you're wondering or confused about goodness of fit as it relates to those numbers and those metrics that software packages throw out, you need to learn more about what goodness of fit actually looks like. You need to develop your own confidence in understanding what a probability plot looks like, what it means, what it's supposed to do. Because if you're asking those questions, you don't have confidence in your own skills. That's the root cause of this issue. You need to develop those skills.
Yeah, well, I think the bigger issue is that people don't even ask those questions anymore. They get an answer in a plot, and not even a plot. They get an answer and it goes, oh, it's a beta of 2.4, and they're off to the races. And I'm like,
yep.
Wait a minute here. Let's plot this. Just take a look at it. Oh, this doesn't make any sense whatsoever. And how could that happen? The software is, it's really fancy and it's using all these cool algorithms and everything else. Yeah. Yeah. So.
And we haven't even talked about the number of data points you have, the amount of information, because you could say that, well, it's raining today, and that's the only piece of information you have about that particular place you've currently parachuted into, or what have you. So your best guess about what's going to happen tomorrow is that it's going to rain. Mm-hmm. But the only information you have about that place, because you've never been here before, is that it's raining today. So that is your best guess, but it's a very weak guess. And so that's where, if you have 3 data points, you can often get some really fantastic metrics that the software spits at you, because those 3 data points can fortuitously fall on roughly straight lines, regardless of what model you use. But if you only got 3 data points, you really don't have a ton of confidence in any conclusions that you might make.
Yep.
And that's, again, comes into the experience and the skill set of the person doing the analysis.
Well, that's probably why statisticians get a bad rap, because we almost always say you're going to need more samples than you think you need.
Yeah.
You know, but what do you mean? I got 2 points. It's a perfect straight line, and we're done. Let's make a model. Let's go to production. I'm like, well, you might not want to do that. You know, let's talk them into another point, and oh, okay. And sometimes it is, yeah.
But on the flip side, if you need to demonstrate, a relatively high reliability at 1,000 hours, and your 2 data points include a time to failure at 12,000 hours and another time to failure at 13,000 hours, i.e., well and truly past your goal of 1,000, those 2 data points might be enough for you to get the confidence you need, because they are so far beyond what your goal was.
Yep.
It's all about context.
Yeah. Now I had one case that I was teaching a class, and we were doing reliability statistics type stuff and some SPC statistics and some other stuff. And it was a little bit of talking about confidence. And the question came up of sample size. And so one of the ones that we almost never have direct control over is the variance, the standard deviation type element of it. It's a characteristic of whatever system or, the parts that we're measuring. And so, and they wanted to have like 99.99% confidence and a very tight measure of perception of change. And like, typically that's a recipe for, gazillion samples.
Mm-hmm.
And we ran out the calculation, and we pulled some of their existing data to estimate the variance, and the variance was so small. These guys it wasn't intended to be precision parts, but the variance on them was in the point, the tens of thousands decimal point. It was way out there. They almost were beyond being measured as different. I was worried that we were going to run into being attribute data, but they could measure it very well to like 3 points of accuracy beyond, so it was obviously variable data and years, weeks and weeks and weeks of data. And it was like, how in the world? And we did a measurement system analysis on it, and their measurement system was good, really good. And so we ran out the calculations, and they needed 0.6 samples. I don't know. Is that plural when it's a fraction of a sample? But shades of my English teacher, I guess, today. But
right. Yeah.
But the idea is that, sometimes the model and it fits really well because it is behaving very well. It follows that pattern really well. And the metrics all look great. But I still want to see the plot. I still want to see the underlying, what's the logic of why are we picking this? Versus just that the software told me that, or the calculator told me that, or whatever. I did convince these guys in Korea that they needed at least 2 samples because.
But there again, I mean, and I talk about confidence. Confidence is not a measure of your device; it's a measure of you.
Mm-hmm.
And you and I both know the organisations who tend to do better than others are those who get confidence from not from statistics, because if you exclusively rely on statistics to get your confidence, that means you are generating no confidence from your understanding of the underlying process. So there are plenty of organizations out there who design really reliable stuff, and they know they're designing really reliable stuff because they work so hard on having a robust design process that targets the vital few and all the other good stuff we keep banging on about in the other podcasts.
Mm-hmm.
And when it comes time to production, they know that their things are so reliable that they don't even worry about these demonstration tests that lots of other organizations seem to crave.
Mm-hmm.
And the reason why those organizations crave those demonstration tests is because they don't generate confidence from having robust design processes. It's all standard driven, or you know what the issues are.
Yeah. Test it in at the end and ignore the bad results. Otherwise, you can't ship.
Right, because they didn't invest in any of the in designing, making their first designs reliable designs. And so that scenario you talked about, where you had that company that had to demonstrate compliance and only needed 0.6 samples.
Yep.
You also talked about how you generated confidence from not just the statistics, but you investigated the measuring device to make sure that, these unbelievably great results weren't an artifact or an error in the measure. You generated confidence through so much more than just a simple number.
Well, it's part, and it was Wayne Nelson. Early on in my career, I was working through his books and doing accelerated testing, but also got to talk to him quite a bit. And he goes, he says, why is it that your book lists the assumptions? And then I spend half my time checking the assumptions. And I told him the story and I'm glad you did, because the ovens we were using, used forced air to move the air around and around our samples. And they were at, 300 degrees Celsius. I mean, they were pretty hot ovens for the testing we were doing. But one of the assumptions was that every sample got the same temperature. And so I put a rig in there with a bunch of thermocouples on it and found that it was almost a 75 degree Celsius difference from high to low within the oven, depending on where it was. And so if I wanted to pass the test, I'd always put my samples on the lower left side, kind of thing. And he goes, there's only so far I can, what Wayne would say is there's only so far we can go with statistics. You have to actually understand what you're doing. And underlying statistical assumptions is just part of it. There's all the engineering assumptions also. And so we make all these assumptions that it's homogeneous, it's this, it's that, they're independent, but check it.
Right.
Here's the techniques to go check it and go do that. And I learned early on, and it just reinforced my mistrust of calculators that I learned in high school. But it's a way to look at the regression metrics is, they're a piece of the puzzle. And as I just said, how high can you jump is jumping relevant to what you're using this model for. Or how it's going to be, how does it actually represent your data, your performance? So all good stuff. So I'm just thinking, I just got, one of the thoughts I've had recently was, is get a couple sets of just data, just random sets of data that I have railing around, sanitize them, and ask our audience to go do the regression on it. And why do they fit what they fit to it? And part of it is this, because I remember years ago seeing differences between different software packages. If you just did all default, you would get different answers. But how do you apply, here's the scenario, the story of where this data is from. How would you fit data to it? And then what would you do? I'm curious if that would be of interest to this audience, if we did a study like that.
Especially the software bit, where we have, different Weibull plotting software, for example, giving us different estimates on shape and beta parameters. And the other thing we could do is have like a deliberately small set of data, and I could secretly generate the true confidence bounds using the.
So it's not secret now anymore. It's not secret anymore.
Well, you know what I mean? Yeah.
So there is an answer, but what does everybody else get? Kind of thing.
Yeah, well, the confidence bounds that are based on assumptions, as you know, they are what they are.
Yeah,
it's just they're not good.
Yeah. Well, it's also, I'd be curious to see, just the thought process. How do you know that this is the right, given our discussion here is like, well, how did you go about doing this? Is it dump and chug, dumped it in the software package and get it, which is a technique, or did you do this or do that, or what'd you look at, or what other follow-up questions do you have? Make it like a reliability statistics combo. See how many people could fit a Weibull in 3 seconds or less. Yeah, something like that. Well, anyway, let us know if you think that would be a cool idea. It wouldn't be, I don't think it'd be too difficult. Generate a couple different scenarios, and then we could take a whack at them and see what we get, what kind of differences we get. And that might make an interesting little discussion and paper type thing. So let us know. Head over to accendoreliability.com/go/SOR, and you can leave us a note there or a message. And Chris and I and the other hosts are available through LinkedIn or through our About pages. Lots of different ways to get in touch with us. And we let us know if this idea for a quick study of doing regression, in your free time, of course, would be of interest. So we'll see what we get on that. I might just, start. I'm already thinking about this, but I really don't want to put it on my list of things to do today. I better get some other stuff done.
Well, it is Friday our time.
Yeah. And I'd like to get that done so I don't work all weekend on stuff. I like to get a few other things done around the house. So as it goes, all right, Chris, well, let's go out and do some data analysis and do it properly and all those good. Do our maths well.
Absolutely.
And all those good stuff. All right, cool. Have a good
what we do.
Yeah, definitely. And so have a good weekend, Chris. We'll talk to you again soon.
Always a pleasure, Fred.
Cheers. Thanks for listening to Speaking of Reliability. We invite you to join the conversation. If you have a question or a topic that you think we should discuss in a future show, please let us know. You can find a comment box below the episode show notes, or just leave a note as part of a review on iTunes.